Hello, everyone. Oh, we're going to do a bit more advent of code with differential data flow. In particular, there was a Hacker News post that talked about Day15 and speeding it up using algorithms and stuff like that. And I couldn't help but notice that it looked like a problem that fit really well with differential data flow. So I figured we'd just give that a spin and see what happens. In particular, there's the exciting bit of drama that apparently part 1 is fine or something like that, and part 2 is where things get interesting. So we'll have to see. I don't know what part 2 is yet, so we'll have to see what happens when we get to that. We'll see. So roughly skimming what Day15 is, I haven't. There's a plot. I don't know, something about submarines, but the idea, at least for this problem, is that we're going to try to navigate. We're in a submarine, and we're going to try to navigate around, and we need to move through a square. I'm guessing from, I think it's the upper left, the top left position. You start in the top left position, try to get to the bottom right, and there's some risk integer associated with each location. So we're going to move from the upper left to the lower right, taking steps that are up, down, left, or right. And we add up all the numbers of the squares that we enter. We don't add the starting square, but that's fine because we always start in it, so it doesn't make any difference. Of course, we always end, I guess, in the ending square, so that's also silly. But yeah, the goal is to find a path, and you can sort of see if you look really close over here. There's a path 1 1 2 1 3 5 1 1 5 1 1 3 2 3 2. A bunch of low numbers, which walks your way through. The grid gets to the lower right, and your goal is to find the path that minimizes this. You're usually going to go down and to the right, though there's no particular reason that it has to. And we're going to get a puzzle input, and we need to figure out what the answer is for the lowest total, going from the top left to the bottom right. And the puzzles look like this. They're a fair bit bigger than in the example, but we're gonna use the example also just to make sure that we don't get some off by one errors or anything like that. So that'll be our input. I have the previous little bit of programming that we were doing here. We got up to day 3.5, or halfway through day 3, I should say. But this seems more interesting, so I'm just gonna copy over some stuff here. Day 03, we're gonna make into a source bin day15.rs, and let's pop open day15, and no, we still had day15 from 2017 also. It's exciting. Okay, our input is again going to be a giant vector. Oh my word, I forgot how big this is. That we're going to delete here, and actually these inputs are a bit more approachable, right? I mean, these small ones are fine, and even the bigger ones is not 1,000 lines. It's just, and probably the right way to do this is still just to treat these as text and parse them out. I'm not really sure of a better. We could vec them out. Well, let's see. Wasn't so bad. It's gonna be terrible to do. Okay, sorry. Yeah, it's gonna be terrible to do on the. Or it might be very soothing to do on this thing. Yeah, we'll do the same thing. So these things are locations. We're going to need to get some sort of XY coordinates out from them, and then this is the cost associated with it. So we're going to use, I think, probably a fairly standard representation, which is our collection of data are going to be triples of row, comma, column, comma, value. And we're going to repeatedly, well, we're going to do some stuff, basically. So what are we trying to do? We're trying to get from the upper left up here to the lower right. And there's a few ways we could do that. And we're going to start with the easiest way, or the most direct way, let's say, in differential data flow. We should start at the goal and start to walk backwards, basically, and say, well, it's super easy to get to the goal from right here. It doesn't cost us anything. to get to this goal, knowing that we have a viable solution of cost 0 right here, we can propose a solution to each of the neighbors, this 8 and this 1, that says, well, the two of you happen to be right next to me. You can get to me at a cost of 1. You pay the cost to go into a square. So propose a 1 to each of them. They now write down, amazing, I could get there with a cost of 1. You repeat the process, sort of growing outwards, and this square, this 2, for example, would get a proposal, 2 proposals, actually. It would get a proposal of a 9 from below it, saying, you could get to me for 8, and then I can get to the goal with 1, and a proposal of 2, 1, and then 1, and it will take a minimum of these things. And just remember the minimum. It doesn't really care about the 8 anymore, and it's going to totally forget that. However, the 5 over here is going to have to use that path through the 8 if it wants to, for the best path that it has to the goal at this moment in time. And this will sort of grow outwards as a wave. You can sort of see it'll grow outwards, and values will start to stabilize in terms of, often the very first proposal will be the best one because it's the fewest number of steps. But there could be paths where a slightly quirkier, low value thing winds its way around. For example, I'm looking at like this number here, this 1. Could go down into a 7 here, but maybe it's a little cheaper, I'm just making this up, to wind its way around to the 1, the 3, the 2, and the 1. That's still 7. Anyhow, there are cases where you might be able to skirt around a big number by taking some smaller numbers as you go. So let's try to implement that. And sorry, this will iterate to a fixed point, and then we're going to be interested in reading out the 0, 0 location. And that's it. So we'll try to start sketching that. I'm not going to worry too much. Oh, we'll see. I correct the comments here. Risk. Great. So we've got per work. Well, sorry, this is timely worker parameters. These are things that can let us load the data potentially a bit more efficiently in parallel. If we pull out only, for example, only elements of input whose index lines up with the worker's index, that partitions the data loading across all the workers. This isn't a very big deal at the moment. So we do need to, we don't even need to, I was going to say we need to put in only 1 copy of each thing, but I think in fact since we're doing this minimization, if we have 4 copies of the number 2 here in this location, it doesn't really matter. But try to be good people. All right, so we've got this input. We're going to, I guess, we're going to clone it and iterate it. I never figured this out last time, how to tastefully own just 1 copy of this and let everyone read it. And it's probably something horrible, like putting an arc around the whole thing so that the lifetime is guaranteed without cloning. But we'll just do this. Well, sorry, we need to do a bit more because it's not just strings anymore. So let's have our goal here of getting risks down and all the risks. Let's have each of these be a row, column pair with a value. And we're doing this because the row and the column, we're going to want to do some joining and some grouping, and we'll always want to use this pair as the key. Right? We're not going to be aggregating across entire rows, yet at least, across entire rows. Really, it's just, these are the nodes, if you will, in the graph, and there's a grid as the sort of the ambient sets of edges underlying the graph. So what are we going to do? We're going to take the inputs. We are going to clone the whole of them. Again, just ignore this. We're going to enumerate this. This is going to give us this list of columns, essentially columns, because we're iterating through the outer thing, and vectors. And I think what we want to do here is flat map this. Or we could filter it just fine here. But actually, we'll write some things that I think we could do either before or after we do turn it into a timely data flow. But I'll write them just here. This is just Rust iterator code. So we filtered so that the rows are now partitioned across each of the workers, and we're going to do a flat map at this point to take the pause is wrong. Let's call this call. So a call indicates an entire row. Is that sorry? So this is the y coordinate essentially, which tells us the row. And we're going to take a row and a vec of these things, and the flat map is what allows us to take one element, a row and a vector, and turn it into multiple outputs. And to do that, we're going to vec.into iter, and we're going to enumerate it to get columns, and then we're going to map column and the value. And we need to put a little move in front of it. Map the column and the value to a row and a call and a value. So just to sort of state again, or I could indent this way and break this down. We've got our list of rows and vectors partitioned up across workers. And for each of the row and entire vector of its contents, we're going to turn it into a bunch of sort of atomic measurements, where each of the records is now one of these risk measurements identified by a row and a column and the value there. So we take a row, we take the vec and iterate through it, put some column identifiers on it, and spill out all of the different values at each of their corresponding rows and columns. And we just need to take this whatever this tuple is. This is turning it into differential data flow land. If you recall, we had some data here. Differential data flow wants us very much to tell us not just what are the data, but at what time should we do a thing with them, and what should that thing be. So we're just saying at the moment there's no concept of time here, and there probably will remain no concept of time. We'll see. But if we wanted to, for example, change these risks, and actually the algorithm is going to, I think, be very amenable to incrementally updating. But if we want to change the data, we might use time 0 or something like that here. And the one is just saying all of these measurements go from, well, having an occurrence of 0 at this state. Everything is an occurrence of 0 at the very beginning of a computation, and we want to add 1 to each of their occurrences, so essentially introducing or inserting each of them. Great. All right. So I think this sets us up with some input data. And we had a whole bunch of crazy code there. I'm just going to delete that so no one's confused. I don't even remember what it was. Part 1, path from 0, to the other end. I suppose, I mean, one thing I don't know, we haven't figured out yet, is how big this thing is, like what the largest position is there. I wonder if we could go and find this, we could start from 0, and spill outwards if we wanted to. That would be backwards, and we'd have to change our logic, because the cost of going from, okay, these are all 1s, but the cost from going from 1 to 2, for example, is 2, not 1. Maybe that's fine. Well, we could go in both directions, for sure. And sorry, the reason I'm mentioning this is only because it's easy to start at 0, because we know what we're looking for, and then it's potentially easier at the other end to say, great, now that we've found all of these things, what is the largest the largest of values, which we could just read out all the values, or we could just, the largest of indexes of rows and columns. We could also just capture it here, I suppose. Right? Like we could. This is not particularly immoral, I don't think. Did I get that right? No, I probably screwed that up, didn't I? It's backwards. So rows, there's a row for each of these, right? And each of these have an entry for each column. And in some world, we could ignore this, start at 0, 0, up in the upper left, and let the data reveal this to us. But we're not going to do that. I'm trying to think, actually, sorry, I'm just scratching my head a bit about why not start here and flow forward rather than start at the goal and flow backwards. I wonder if there's a good reason. It feels more natural, I think, for a lot of folks writing these algorithms to start at the point of origin and move forward. But well, we'll see. Or yeah. I guess we'll start up here. Let's start at 0, 0 and just flow forward. So what are we going to do? We're going to maintain a collection of reachable locations, so 0, 0 is, I guess, where we're going to start. Reachable and their associated accumulated costs, and we're going to iterate. Basically, we're going to put together some iterative computation here. So we want to start with a collection, which I'm just going to let be. What is the collection that we want? It's going to be 0, 0 that we start with at distance 0. I'm using sum, sorry, because it's going to be, I think, did iter once. Basically, iterator that contains a single thing, which is the row and column, and then the accumulated costs. And we're going to want to turn that into a differential data flow collection, which, again, we might want to, this is sort of silly, but we want to only do on worker 0, otherwise we'll get a few copies of this initial starting point. I think that would be totally fine, again, because we're going to take these maximizations at each step, but just to spare us. And we need to do the same sorts of things that we've done here, toStream and the mapping. Actually, I should have a break there. Yeah, it's still a tuple, but I'm just gonna call it start to be clear. Or maybe I should call this start, sorry. And we'll call this tuple again. And what we're gonna do is we're gonna take start and we're gonna iterate forward. So we do start dot iterate. And the way iterate works in differential data flow, though I haven't written one of these in a while, this is going to return returns the collection of all reachable locations and costs. We start our iteration from some collection, in this case start, whatever we choose to invoke iterate on. Inner is then a little bit of a placeholder that says, well, if I were to give to you the current state of affairs, whatever the current iterate is, current version of the collection, initially start, but it will evolve. What would you do with it to produce the next round of iteration? Right. So if we had some reachable set of states, initially 0, 0, but whatever, row, column, and value things. What would we do at the next step? Well, we'd probably look around at the neighbors, and I'm thinking what we're going to do is we're going to advertise. Everyone who's reachable is going to advertise at each of their neighbors, hey, look at me, I'm potentially reachable, and that's super exciting. So at which point all of these advertisements will reach the nodes. The nodes will then say, amazing, I've got lots of options now, or potentially up to 4 options. I'm gonna choose the best one and call it, and then take a little rest. That'll be the next iterate. And this process is the process that will continue repeatedly and hopefully reach a fixed point. We can sort of see in this example all the numbers are non-negative, for example, so it should reach a fixed point because the proposals will only go up. So let's do that. And I'm a little hesitant actually now because when we do this join, so this is this difference between going forwards and backwards, maybe, which is when we do this join, what are we going to find? We're going to find the cost associated with a location, and this location is almost certainly going to propose at each of its neighbor 4 locations. So it's going to look at its row and column and mint new candidates that should be sort of circulated. When we do the join, what we're going to get is that measurement and this value, right? We'll get an 8 in this direction. Just that happens to be the value attached to the location that we're joining with. Is that appropriate? I guess that does say, that does say if we add 8 to whatever it took for me to get here, that's the right cost standard. Okay, sorry, this is totally fine. I was a little worried that we wanted to ignore this but maybe that's in the opposite direction that happens. When we went out to this 8, we didn't actually care what that 8 was until we take the next step. But maybe this is fine. These are the sorts of things that it's easy to get wrong. It's just little, when do I put certain pieces of data together? So inner, the intent is that inner has this structure that we had before, row, column, value. And so all we're going to do, I think, is inner.join with risks. And because of things, we have to enter risks into the inner scope. Right, so risks is currently a sort of static collection that certainly doesn't change in the course of this iteration. We need to warn the system essentially, like I'm telling you about a collection now, and you may be surprised to learn that it's not actually in this iterative context. So, and we'll see if I need some references around that in a moment. But basically, we're going to join these things together, and then we'll do a little map on the result. So the result of this should be a key, which is, I've got a few more things. I screwed this up. Let's do this map for the moment. So before we do the join, apologize, we have to map the row and column and value pair to 4 new candidates. So we actually need to do a flat map. 4 new candidates, right? So each of the locations that can be reached is going to propose at 4 other locations. We're going to ignore the fact that you can't propose, proposing off the border is a bad use of everyone's time. That's fine. We just won't match any, we won't join with anything over there. So what's going on here? We're going to flat map this row, column, these parens, just make my eyes bleed. And what are we going to do? I'm going to try to do something. We just want to put together 4 things, don't we? So we'll just do the back. This feels gross doing these things, but do which is going to be row and call and val. 4 of them, each with a row and a column modified just a little bit. So row +1, call +1, row -1, and call -1. I believe these are the 4 ways that you can move around. The value is unchanged. The flat map just needs to produce an iterator, something that can be turned into an iterator, and I've said go and allocate a thing, though at some point in Rust we should just be able to do a slice. I forget if we can do that now or not. But let's just do this to be a little sloppy. We'll think about performance later if it matters. All right, this we can now join. Right, each of these results are still a row call and a value. We can join that with our risks. And we're now just going to do we're going to add together some things. So the result of a join should be a pair of the key. The key in this case is row call, and the matching values, which is so far and this square. And what are we going to do with these things? We're just going to turn these into a new measurement. Same row and call, we're not going to change that. And we're going to add together square. I need to typo there. And this is absolutely a thing. There are versions of join that let you put this little map logic into the join itself, because there's no reason to wait until after you've done the join to do this. You can sort of do this action as you go. Followed by a reduce. So for each of these row call things, there's maybe 4 proposals going on. We want to 4 is going to be the wrong number, you'll see in just a moment, but there maybe 4 things going on, so we want to think about taking them all together and saying, for each of these keys, each row and column, reduces sort of the map reduce analog that says for each key and a collection of the input, please populate some output for me, and I'll make that be the result. And what we're going to do is just take the minimum of the inputs. So I think this is just going to be output dot push of input 0.0 1, where what this is saying is input is a slice of the values, essentially. Each of them, in fact, is going to be a value and a count. So we might, if we have 4 copies of number 3, we will get a 3, 4. So value and then the number of times it occurs. So we just want the value. We only get presented with non-zero values, and we know none of them will be negative. So we'll just take the first one. They're sorted, put in sorted order. So the minimum, great, is just going to be the first one, the 0th. And we announce this with a count of 1 in our output. And we might, at this point, be done. Now, I happen to know that we're not, because we've forgotten a very important thing, which is that we need to reintroduce start to this thing. Right, we want the upper left corner to stay an option, right? If we did these joins and then say, great, now do a reduction, there wouldn't be anything for 0, 0 anymore. It would go away. And that would suck, because in the next iteration, the 0, 0's proposal to everyone would also go away. And you'd have a wave sort of move through the grid, but not actually stick around, so it wouldn't necessarily reach a fixed point. And that's not so bad. That's just a matter of concatenating in our starting collection again. So making sure that this remains, whatever our options are that we produce through the joining, also give everyone the option of staying how they were at the very beginning, which only really matters for 0, 0. Great. And in principle, this might do a thing. Before we try to actually read out any answers, what this will hopefully do is produce a collection that we could inspect. The curly, the parens and curly braces don't really line up great. This is the iterate there, but we can put an X there, and this will tell us all of this is what, like 100 or something like that. No, not quite, but no, exactly 100. 100 measurements that we've reached. We don't really want to look at all of those, so we'll put a filter in just a moment. But let's see if we can get the code tested. All right, inner.plot map. Yep. A bunch of just grammatical errors here. Bunch more grammatical errors. Okay, so these enter needs references for reasons that escape me. And join needs a reference. Lots of these things need references. Basically taking ownership is annoying with timely data flow because the stream's then gone and you can't use it again, even though we know you should be allowed to. Expected integer found out. Yeah, great. So this is a reference actually to an integer, so we should dereference it to actually get an integer. And index does not live long enough. That probably makes some sense. So we'll need to do a move somewhere. Line 47. Wait, hold on. There is a move there. What am I missing? Oh, this is going to be another one further down. Sorry, 59. Great. And we can tidy this up a little bit. We ignored rows and calls, so that's made it a little frustrating. We don't need to pay attention to key because the reduction logic is going to be the same for each of these things. And other than just, cargo run this, I'm just sort of curious to see the shape of the output. And then we'll filter down in just a moment to see if we get the right answer. Actually, we can look at the answers here and hopefully see that we got the right test answer correct before we... Oh dear. Sorry. As we try to walk off of the grid in debug mode, because these, I guess, are unsigned integers. Oh, they are because these aren't, I have no idea what integers these are, but our enumerates are unsigned integers and don't wrap by default. And hopefully, yeah, great. So 40 was the answer we came up with. Let's see if 40, I think 40 was a number that I saw down here. Great, 40, amazing. Well, and you can see a lot of stuff here. Actually, let's tidy this up a little bit. You can see some negations, for example. What does that mean? Almost certainly what that means is that somewhere else we saw a 1,8. Sorry. These two together represent a correction of 1,8 previously being 37, which actually you can see right up here. A correction of 1,8 from 37 to 32. And we're seeing all this because what iterate produces is the stream of all the changes that occur, and if we want, we can put in a consolidate here, and that will not allow us to propagate any of the changes that cancel out. So it'll make sure that all of these are, yep, great. Still seeing a 40 there. So let's put in a filter here, where we look at the row and call and don't really care about the value, and ask that row plus 1 equals rows, and call plus 1 equals calls. I don't know if I have to dereference these or if, yeah, great, all right. Oh, right. Just make these eye size also. As is a naughty conversion to use because you can't really tell if it errors. Lifetime may not live long enough. That's right. We need to go and take these integers and move ownership into those closures. Great. And we see here the 40 again. So let's grab another more grown-up input. See how painful this is. Yeah, it's juicy. Though it's not epically sized, right? I can't tell how big it is, but it's not 100 by 100 or anything. Is it? Okay, we'll be able to do the math really easy actually with maybe it is 100 by 100. So we are here, we're going to do vec. Then we're going to do a whole bunch of this stuff. which isn't meant to be visually stimulating for any of you, but is feels really great. Like, look at how much productive typing I'm doing just by pressing two characters back and forth again. Two keys back and forth. Mentally, it's really complicated not screwing this up, as you can see. Almost there. Alright, we're at the end, so at the end of the little vec thingies. And I think this is correctly structured now. Let's see. Alright. And it took a little longer, you might notice. I'm just gonna try to release build while we go and type in 508. Is our answer? Cross fingers here. Oh, nice work. All right. Maybe what we should have checked. There's a 9 this, and there's a 7 up here. So we actually did get the math right, as far as I can tell, about which of the beginning and ending points to include. That's great. This is going to take a little while to build. While this is building, let's check out part 2. All right, so, okay. Entire cave is actually 5 times larger in both dimensions than you thought. It's actually a 5 by 5 map of the 100 by 100 things we're looking at. The original map tile repeats to the right and downward. Each time the tile repeats to the right or downward, all of its risk levels are 1 higher than the tile immediately up or left. Okay, sorry, so this just means, I think, that we get original copy, and then below it and to the right, it's all those values plus 1. Below those and to the right again, all those values plus 1. Sorry, I'm just trying to read through it. As a risk level is above 9, wrap back around to 1. Ooh. So the problem is bigger and more complicated. And we still want to go from the upper left to the lower right. So I think this, okay, it sounds like this is mostly a test of, is your algorithm not terrible? Which is a great question. We'll have to see. So this, is not fundamentally different. Okay, so seems to go relatively quickly. I'm not actually timing that, but felt largely interactive. So what we need to do is just produce some more input data, I think, right? Like, we need to take our original collection of input data and do some flat mapping, I think, right? So rather than, all of this stuff is going to be the same. So we are not going to worry too much about that. We're just going to increase the size of risks. So we're going to let big risks be. And what we want to do now is there are going to be 25. So each of these little doodads, I have to call them, sorry. Each of these risk measurements is going to produce 25 other risk measurements at their location and various multiples of plus rows and calls, right? Where we add up, if we add I times rows and j times calls, we add I plus j, add those to all of the risk measurements because it goes up by 1 each time you go to the right or down. And then take them, not mod 9, how does it that work? Wraps around from 9 to 1. So mod 9 actually plus 1. Does that sound right? Probably not. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9 is, these off by 1 issues are tremendous. So a 10 should not be a 10, it should be a 1. We'll figure out the math for that. yeah, that's definitely what's happening. But so we've got a little bit of logic to get right here, but fundamentally there isn't a new algorithm that we're going to do, at least not at this point. There is some cool stuff to do here with respect to efficiency, and maybe the data will get big enough that it's actually going to be important for us. But one thing we should not think to do, maybe this is a classic trick, is try to reuse our solution, right? Like we found a path from the upper left to the lower right. That doesn't mean that the paths from, within this 25x larger thing are going to be from the upper left to lower right of individual subregions. They might cross halfway through. Those big 9s in one thing might look really appealing, and once the count's been bumped by 1. So yeah, let's want to be careful. I think the easiest way to be careful here is just to make the bigger input, run it, and see if it takes too long. If it takes too long, then we'll get a little stressed out, and we'll try to think about how to make it better. But all right, how do we want to go and produce this? So we're going to just take risks. I'm going to say we're going to do a flat map where we have row, call, and val, and we're going to want to turn each row, call, and val into a bunch of stuff. What's that bunch of stuff going to look like? It's going to look like 0.5. These are going to be the we'll figure it out, rows, let's say. But sorry, we're going to try to write a for rows equals 0 up through and including 4, for calls equals through and including 4, and then for each of them produce some output. So we're going to iterate through 0, 1, 2, 3, 4, and for each of them we are going to want to be like row incur. For each of them we're going to want to pick out a bunch of columns also. Which will be call, incur, and these are going to need to have moves in front of them, of course. Now, for each row incur and column incur, we're going to want to produce, I believe, an output that looks like row, which is the row from our initial measurement, plus row incur times row, hold on, do we add, okay, sorry, so this is the total rows, is the thing that counts up going down in this direction, and also the thing that identifies them, so I think we add multiples of rows to the row. Oh. Same thing with call. So this is our key, and now we need to put together, structure these things better, put together a new value, and that value I believe is going to be val plus, how do we want to, we add up basically val plus row incur plus call incur, which is the number of times we've stepped val upwards, so it could be just val. And what we want to make sure that it does is that it stays in the range 1 to 9, where we do some modular arithmetic. And this is all probably terrible, but we want to subtract 1 mod 9 plus 1 is, I think, the right logic here. Those parens balance. If it was going to be 0 up through and including 8, we would just do mod 9. And we could sort of think of this as all being 0 up through 8, except for the fact that that totally changes the answer, because having this initial 1 on every step makes a step expensive, right? Great. Big risks. Actually, we'll just call it risks again. It will shadow, and that's maybe not a form, but this at least. And we don't really care about the answer now to to rows and calls, we care about the answer at 5 times. So I'm just going to keep a second copy of this so that we can go back to it if we need to. I have zero confidence I understand these sorts of sorry, I'm trying to be a bit more clear. Great, this is the part 1 targets that we're using. And we'll have some part 2 targets that should just be 5 times. These can simplify our logic down below to be just testing for equality rather than plussing. Though we might have to do some dereferencing. Let's see. So we're going to cargo check things. There's some let risks equals are giving you a semicolon. That's a great point. This is this not a range? I'm sure I botched something hilarious here, but we'll oh, okay, sorry. I think this just means we need to do std iter, or sorry, we can make the second one just be a map. It doesn't need to be a flat map. It's probably not the only issue though. Great, actually it's relatively few remaining issues, so we should dereference the rows and columns. And lifetime may not live long enough for we also need to move up there. Perfect. Great. Unused variable target. Oh, this is the preceding ones. That's good that it reminds us. Let me delete the filter here. So we already saw actually that the debug version was slow, or it was starting. Actually, sorry. So we should comment this out for the moment and check to see if we get the right answer on the test data. Where the test is going to be 315 is what we're hoping to see. 315 is indeed what we see, so maybe that means we got it right. So what's going on here? We got it right despite the fact that we put in this 5 times thing, which I'm not at all happy with. Oh, wait, no, I'm sorry. That was exactly right. We were just screwing out the inputs. That wasn't actually, this isn't a part 1, part 2 distinction. This is just test versus real data distinction. Great. So let's time this. What? Oh, bother. Why did I botch? I took out a thing that I wasn't supposed to take out. Filter comma. That's ridiculous. All right. And it's going to rebuild, so the timing is not nearly as interesting. But we're going to do a little timing, and I don't think it should be much more than 25 times slower than before, which actually that might be a minute or 2 or something. This could be pretty boring. La la la. Debug Rust and released Rust can be very different in terms of their running times, especially with closure-heavy programming, where a lot of the gobbledygook here can get reduced down to very simple code through optimization, but if you have the optimization turned off, that doesn't happen. All right, how long do we wait? We're already kind of bored. Yeah, we're gonna stop. I'll go back to the release build, which will take a little while to build. But then when we ran it before, it was quite fast, and it shouldn't be much more than 25 times slower than it was before, which hopefully is just a few seconds. But we'll watch it build for a little bit. Oops, interrupt the thing and start it again so we get decent timing. Also slow. All right. Did I not? I didn't even time it that time. I'm sorry, I apologize. But we got an answer out. We'll have to see if that's the correct answer. Great. Let's check it out. It took about 10 seconds. Hooray! All right. So differential Dataflow gets you correct answers. Just heads up. Now, we could stop here. That'd be fine. But there's a cool thing that we can do that I'm curious if it actually makes the performance better. This is a thing that you definitely see in problems like this, where you're trying to navigate a graph, and the graph has costs, and you're trying to find the shortest path. Which is that the process by which differential data flow and most iterative algorithms is going to explore the graph. Let's just look at the this example. Here we start up here, and in one step we'll hooray, we'll have opened up 2 more squares. If we go again, we'll open up 3 more squares. And if we go again, we'll open up a 4th square here. We'll have 1, 1, 6, and this will propose an 8 at this 3. And that's fine. I mean, nothing's fundamentally bad about that. But it might be a bit premature, right? We're still very much, like, we could go 1, 1, 2, 1. There's really no need to start talking about 8 yet to anyone, right? Because we're still sort of in this accumulated 4. We can make it all the way down to here before even needing to propose an 8 outwards. And this is good for a few reasons. What I mean is, if we can find a way to slow down the propagation of information, to say, like, hey, you don't need to, in iteration 3, you don't need to go and start talking about 8 already. Feel free to wait for a little while. But what's a good amount of time to wait? Possibly till round 8, actually, because we know that these counts go up by 1 at least each time. If you wait till round 8 to tell us what's going on, that's going to save us a little bit of thinking. It'll cost us a little bit, but it'll save us a little bit of thinking. And one thing that'll definitely change is it will reduce the churn, right? It'll reduce the total amount of changes that happen in each of these rounds of iteration. This is a classic problem in big graph stuff, which is that essentially it's like parallels to the modern world, but bad information can flow very quickly through these graphs. Bad information being answers that aren't going to be the right final answer, but they make it pretty quick, and they need to be corrected in the future, and anything that needs to be corrected has this defective property, unfortunately, that the erroneous thing is going to keep flowing, and you're not slowing it down at all, so the corrections are going to be chasing it, doing just as much work as they go, and it's a big waste of time. And if you can skip that big waste of time, then amazing. So I don't actually know if that's what's happening, like big wastes of time. We could check, though. Let's see if I can figure out how to check. So the intent is, if we take inner as we're iterating, and we could look at the contents of inner and roughly ask how much data is there in each of these rounds of iteration. And I'm not sure of a great way to check that stays sort of on brand. I'm gonna do some gross stuff. Let's see. So if we do inner.consolidate, this is going to make sure that we only ever look at canceled, minimized, let's say, changes to the collection. So we don't see phantom, a plus and a minus that would cancel each other out. But we're going to consolidate this. We'll turn it back into a timely data flow stream by looking at its inner contents there. And then we're just going to blank out the plus and minus ones. We'll turn them all into data time. You say doesn't matter if you're a +1 or a -1 or a 7 or whatever. All those things are basically the same. We'll do data time 1. So you are 1 unit of something that we're worrying about. Turn back into a collection. Actually, we're also just going to ignore the data for what that's worth. Because all we really want to do with this thing actually is then do a count and then inspect. So we just want to say essentially in each time, each round of iteration, what's going on, how much stuff has changed. In fact, we could even skip the count. I think we could just look at the consolidated collection, which will tell us here's how many things added up. And what I'm going to do for the moment is comment this thing out just so that we can try out the debug version of this. Sorry, it's not a function set, it's a macro. Now, we're doing this just to get a sense for the churn in each of these rounds. These are the rounds. 0, sorry, am I looking at this right? It's sort of interesting if this is right. Actually, let me scratch my head and look at this. So we are on, we're on part 2 still, not part 1. So we're doing a 10 by 10 that is expanded out, so 50 by 50. I was wondering why we were counting up to 100. As you can see, as rounds increase, there's some changes. Changes are good. Like changes make a fair bit of sense, right? Like they, we expect in round I to have roughly, I don't know, I or I+1 changes because that's the size of the frontier of like brand newly discovered things. So as long as these folks are the same, or off by 1, let's say, no harm. They're growing a little bit. So here we're changing more than just the perimeter. We're making some changes. We had some wrong guesses that we need to retract. And it looks like this maxes out somewhere at around 2x or something like that. So it's not really that exciting, to be honest. But we'll try it anyhow. I'm curious to see if there's an appreciable difference. 10 seconds, I think, was the number we had before. Maybe we should just do a run with the release build. Or I comment out this. Well, we'll want to do the release build where we don't have this measurement because it's not an inexpensive measurement. But that's fine. We can also put it back in. The release build didn't seem to be so terrible. It's like 10 seconds. Sorry, the actual build process didn't seem to be too terrible. And then about 10 seconds to run. And I don't think we want to look at the results there because that would be, it's not so bad. Maybe it's like 1,000 lines of output. So we run it again to get we're running it with time to get a time measurement. The time measurement is, I don't know how you 10 seconds basically. Let's put this back in, just because I'm curious. We don't really care about the time. I see. Let's reverse that out too. We don't really care about the time because this isn't meant to be performant, but I'm curious to see. This data is not particularly problematic because it has the property, you might notice, that every step costs at least 1, which means that bad information can't get too far, actually, because as it goes, it's always eating a cost of 1. If there are any things that had costs of zeros, for example, that's where things get a little scary, because that stuff flies sort of instantaneously all the way down these paths of length of cost 0, essentially instantaneously. Now, there's actually some appreciable gap. These isn't just 2x. This is substantially more. So there's actually a lot of work that we're doing that is being retracted halfway through. This could have been just 500-ish if we were just setting the correct values at each of these locations. Instead, we're churning a fair bit more than that. So great. Let's see if we can fix it. We're going to comment out the consolidating thing. Now, how do we do this? The trick, essentially, is to take each change that's gone on. Right. So when we get a change, some row column value stuff that says I've changed for some reason, we can do a cute little trick there where we delay the result. So sorry, we delay the update. So it's scheduled to happen at a certain time, right? If we look back at the little bitsy data, there would be a value of 8 showing up in round, 3 or something like that. And we can just rewrite that and say, make that show up in round 8 instead. This change still happens, but it doesn't happen right away. And that will have the effect, essentially, of delaying that update. It costs us a little bit in that delayed update needs to live somewhere. Right? It sort of hangs out for a little bit. Instead of retiring it immediately, it hangs out in some buffer. And we may end up doing a larger amount of different work. And this is a place where some cute data structures could be implemented, haven't been implemented, but could be implemented to better store that future pending work, something like a priority queue. We're not going to do that. But, we probably should. All right, so what does this look like? If, assuming I don't screw this up somehow, we're going to, again, dive into the raw timely data flow stream, because we need to actually screw around with the differential data flow metadata, essentially, of these records. So this is a triple, data, diff, and time. And I'll put in we're going to have data in here, data, time, and diff, I should say, where the data are a pair of row, call, val. I'm sure I've got the parens all wrong now. So the data are an address, a row, and a column, which we don't really care about. Actually, we'll need to reference them to produce the output. Call it val, there's the time, and then there's the diff. And the intent is to take val and basically set the time to be the max of val and time. Let's see if we can pull that off. So we're going to do std conf max of val time. And time might actually be a little careful. We'll see what type gets put together, because it's probably almost certainly like a pair of the empty tuple. It'll be an integer slapped onto the outer timestamp, which makes it not just an integer. But we'll get yelled at by Russ to tell us what it should be instead. Great. So this is what we've done. There's a differential data flow delay function, which might actually be similar. Is this it? Oh, this is just off. Excellent. I'm not sure if delay does the right thing. Maybe it does. What is the function? No, the function just gets to be a function of the existing timestamp, not of the data. Looks like. That seems silly. I should probably go in and try to produce a roughly safe version of this logic where you get to supply this function as a function, morally like as a function of the data, but as long as we take a max with time, I think it's fine. Like you're not meant to go backwards in time. It's highly illegal. So let's cargo check. right? I screwed something up. Map, okay, these things are struggling to line up. Yeah, that makes sense. I think the output of this wants to just be a tuple, not anything of a tuple. It's a data, and the data are these, a time, and a diff, and it's almost certainly, I'm hoping, going to yell at us about the types of the times. Great. All right, so it's trying to compare an I size with a U64. Now, we happen to know that val is in fact a U, well, sorry, it's a U size. It's unsigned because it's not going negative. And even if it were, in some sense that'd be fine. We could, the max will just be the time in that case. So we need to figure out how to interact with these silly things. So we're gonna time dot, I want to call it inner. There's a lot of inner going on, but let's so what we're writing, instead of trying to get the types right, we're just going to say if when we look at the inner coordinate, which I think a product has an inner and an outer. Russ thinks so too. If the value is bigger than time inner, then set it to be that bigger value. And again, as is deeply problematic, we should be using safer casting and all sorts of code like that. But obviously we're not going to do that. So let's try running this again. And we will, depending on, presumably what will happen is it'll be slower for some terrible reason. We'll look at the diffs again. The diffs might be nice and small, but anyhow, let's see what happens. It seemed to go a lot faster. I forget if I got the same answer though. We should double check that. What was the answer that I put in here before? Shit. Okay, well, we'll have to, I don't remember if this is the right answer or not, but if it is, amazing, it goes a lot faster. Let's ditch this new code. I think that's the only thing we need to ditch, right? I forgot about this whole reproducibility thing. Or a little too eager to clear my console. All right, 2872. Those of you watching the video are going to be very frustrated because I'm sure you actually remember what the number is, but I didn't, so I'm just going to jot this down and rerun this with the improved, with the delaying logic, which looks like it's an improvement in this case, if the answer actually stays correct. If the answer doesn't say correct, this is going to be a much longer video. Yeah, great, amazing. So, so hooray! What we've talked through, and actually let's put this back in while I blah blah. We can see a little bit about the distributions of all these changes across the rounds. There may be more rounds now, right? Because whereas previously we would sweep through all of the rounds in the right time, essentially, like in rows plus columns, number of rounds. Oh wow, look at that. That's great. So a few things are good here and some things are bad. Not terrible, to be honest. Actually, this is really not that bad. I was going to say, one potential downside of this approach is that it just takes a lot more time. If there are really big values out there that aren't on that shortest path, we'll still explore them because differential data flow is going to figure out a fixed point for you. And even if we didn't, we could have stopped early because there's a path of all ones that goes directly to the solution and a bunch of nines off the main diagonal. We'll do a lot more work in differential data flow. Here it looks like we didn't end up doing much more. One additional round of work was done after that, basically because the far corner is one of the farthest away points from the original point. If that weren't the case, we'd feel a little bad. But you can see throughout here that we never got those big rounds where we had 13,000 or whatever it was. We do have more rounds, right? So we have about 3 times, I guess, as many rounds. But not, whatever. It'd have to be 130 to get this up to 13,000. So definitely a win there. The total speed up is not. Oof. Okay. There's no reason, of course, to do all of this work. But the total speed up going from, I think it was 10-ish seconds, 9.92 or something, down to what I thought was maybe 2.5 when we ran it. But we'll run it again and find out. Isn't epic, right? It's not amazing. But there's various other things that we could do to try to streamline some stuff also. Get rid of all these silly allocations. All right, so this ended up taking 2.17. We can also we can try some parallelism. No, that made things worse. No idea why. Actually, I'm not gonna even get into thinking about that. Oh, I'm sorry. No, that's I should have been reading the this over here. So this time is actually going down. I've probably just been reading the time wrong the whole time. So 2 point whatever down to 1.7 down to 1.3 as we bring in more workers, mostly because the joins and the reduces are all data parallel, right? Like different worker threads, they just need to exchange some data, and I'd be tempted to. There's other minor nits, like you could try to use this statically formed slice as an iterator, and I don't think it implements Rust's into iter trait, except for some new versions that I don't know how it works. But I'm not going to try to live debug that in front of you. But I hope this was instructive. We learned a little bit about how easy, in quotes, it was to solve this particular problem, where the solution was essentially iteration and this sort of flat mapping, joining, and then reducing. And we learned a little bit also about how to improve things a little bit by changing what's essentially the scheduling of the work in differential data flow. So we're telling differential data flow by editing the data when it should be performing certain actions, and by holding back certain updates, ones that we don't think will be as effectful, we manage to change things less often, do fewer updates that ultimately need to get retracted, anything like that, which I think is pretty cool. All right, thanks very much. Appreciate your time. Cheers.